While background global temperatures are steadily rising, the actual human experience of that heat does not distribute evenly. Down at the street level, physiological heat stress is a strictly local phenomenon. To understand exactly how localized this heat stress has become, researchers conducted a 47-year longitudinal study tracking daily weather parameters from 1969 through 2015. The investigation focused on two rapidly developing cities in the same Indian state, Mumbai and Pune. Though geographically close, they are separated by distinct topography that creates two entirely different climate profiles. Mumbai is a coastal metropolis. Its baseline climate is dominated by hot temperatures combined with a highly humid atmospheric composition. Just 150 kilometers away, Pune sits inland. As an interior continental city, its environment is semi-arid and largely dry. Geography dictates the physics of how heat interacts with the human body, meaning a single, universal temperature metric across these different topographies often fails to capture the full scope of the local microclimate. This outlines the two competing biometeorological models used to measure that threat. On the left is the heat index, or HI. This empirical model quantifies coastal sultriness by combining dry bulb temperature with relative humidity. But empirical models have a strict limitation. They assume physiological factors and surrounding environmental variables remain constant. To solve that, researchers calculate physiological equivalent temperature, or PET. As we see on the right, this model accounts for human metabolic rates and clothing, while adding specific environmental data like wind speed and mean radiant temperature. That last variable, mean radiant temperature, or TMRT, is critical. It measures the total amount of solar radiation that strikes the urban landscape, gets trapped by concrete, and re-radiates outward. To capture this radiation trapping in city centers, investigators map the streets using 180-degree fisheye lenses, calculating a precise sky view factor for the neighborhood. By calculating the total energy exchanged between a human body and its immediate surroundings, researchers can quantify the true severity of urban thermal discomfort using a rational heat budget model like PET. When we apply these models to the 47-year longitudinal data for the summer months of March, April, and May, we see exactly how NOAA categorizes physiological risk. A heat index over 33 degrees Celsius triggers moderate risk, and anything over 39 degrees signals high risk. Look at this set of charts mapping Mumbai's heat index trajectory from 1969 to 2015. The horizontal lines above the trend dictate the +1 standard deviation limit. Notice the data cluster in the May graph. After 2000, Mumbai consistently breaches that upper standard deviation threshold. These specific threshold breaches place Mumbai's modern summer climate firmly into the moderate to high-risk physiological category. The 2010 anomaly makes this even clearer. During that year, recorded as the fourth warmest globally at the time, Mumbai experienced an unbroken season of heat stress resting entirely above the historical mean. Because Mumbai sits on the coast, atmospheric moisture is the dominant force. The empirical humidity-weighted heat index accurately identifies the threat and triggers the necessary public health warnings. Transitioning inland to Pune, we have to ask if the same empirical index accurately reflects a semi-arid urban reality. To find out, we look at this second set of charts, tracking Pune's physiological equivalent temperature over the same summer months. The baseline PET output magnitude here is striking. Throughout April and May, mean averages sit consistently at or above 40 degrees Celsius. In biometeorological terms, a PET exceeding 41 degrees places the population in a state of extreme heat stress. The longitudinal data reveals an aggressive acceleration trend. In recent decades, Pune's absolute PET has increased by over 1.3 degrees Celsius during peak summer. Relying solely on standard air temperature or the humidity-based heat index in a continental urban center like Pune masks the true physiological severity of the street-level environment. To isolate exactly which local variables are driving these PET spikes, researchers applied a statistical method called stepwise multiple regression. This isolates the standardized beta weights for each location, a tool that reveals how heavily a single variable, like wind or humidity, impacts the final heat stress score. Mumbai's heat stress is overwhelmingly driven by wet bulb temperature, the trapped water vapor. But for Pune, the drivers shift. We see high dry bulb temperature, a massive addition from mean radiant temperature, and a steep negative weight from wind speed. That heavy radiant temperature weight is a direct result of urban geometry. Building materials and dense spatial configurations are actively capturing intense solar energy and re-radiating it back onto pedestrians. At the same time, the negative wind speed weight occurs because this exact same urban morphology creates structural friction, deadening the wind corridors required to evaporate sweat and cool the human body. Pune's extreme physiological temperatures are a product of city architecture, a system that traps radiation while blocking the wind corridors required for dissipation. There is a lingering assumption in urban planning that the arrival of the South Asian monsoon reliably neutralizes the threat of urban heat stress. Over 47 wet seasons, these stacked bar charts reveal the monsoon's changing thermal profile. Look closely at the upper chart for Pune. Following the year 2000, a distinct expansion of the dark upper bands indicates an increasing percentage of hot and very hot days. Mumbai exhibits its own specific physiological threat during this season. Humid, dry spells between rainfalls cause intense vapor pressure spikes, creating highly oppressive sultriness even when the ambient temperature drops. In both cities, data proves severe thermal discomfort is no longer safely confined to the peak summer months of April and May. The data shows that urban thermal discomfort is intensifying in severity and expanding across the calendar, altering the seasonal risk profile. Applying a one-size-fits-all metric across differing geographic realities invites catastrophic planning failures. Treating the inland architecture of Pune with the same meteorological assumptions as coastal Mumbai leaves specific, localized vulnerabilities entirely unaddressed. For continental cities like Pune, targeted mitigation requires addressing the variables exposed by the PET model. Planners must reduce mean radiant temperature by integrating heavy tree canopy coverage and architectural shading over impervious surfaces. Secondary adaptations must respond directly to the regression data by restoring urban wind corridors to break up the sensible heat trap. Effective urban climate adaptation requires planners to move beyond the thermometer and design for the complex biometeorological realities of the built environment.